So now that you've seen that you can pull out these deep linear network chains, everything that you've learned about them already, those one-dimensional chains, actually transfers to this more complex setting. All the findings about depth, impact of depth, learning rates, and so on. The only difference is now we have to think of lots of these chains happening in parallel, and of course they're kind of hidden by this. You have to do this particular change of variables to see them, but ultimately they're running in parallel, and then you just sum them up. And so what you're going to get is a lot of drops over time, where each of these chains goes through its transition to lower error at some point in time. So another observation we can make is we can try to line up this error trajectory with the data set that we trained it on. And it's quite remarkable because if you look at it, you'll see that there are 4 levels in this hierarchy, right? 1, 2, 3, and 4. And you'll also notice that there are exactly 4 stages in learning trajectory. 1, 2, 3, and 4. And so it seems like it could be that, in fact, each one of these transitions corresponds to learning one level of this tree. Now, to actually see if this is the case, we're going to have to peer inside the network and understand what its internal representations are doing. And there are many ways we could go about this, but what we're going to do is borrow a method from neuroscience. I mean, it's also been used in computer science, but if you're a neuroscientist, you should be familiar with it, which is representational similarity analysis. So how does this work? Well, in representational similarity analysis, you're going to present an item to a network. It could be any sort of input. Maybe it's an image. In our case, it's one of these sort of abstract items like a dog or a cat. You present it to your network. You run the activity up to some layer that you're going to be interested in analyzing, highlighted in blue here. And that gives you some hidden activity in response to input A. Then you're going to do the same thing again, but with another input, run it up to the hidden layer. That's going to give you the hidden activity in response to input B. And now what we're going to do is compare the similarity between these two activity patterns. So the idea behind representational similarity analysis is it's not the detailed individual neurons that matters, perhaps, but the overall similarity in the evoked activity patterns, which is a function of all of the neurons in the layer. And in particular, here today, we're going to just look at a very simple dot product between the two hidden representations. And that will give us elements that we place in this representational similarity matrix, and then we do that for all pairs of items in our data set. We get back this matrix, which tells us how similar the representations are for these pairs of items. So we can use RSA to better understand these internal representations for the case of this hierarchical data set, and that will be your task now.